Hello class, welcome to the lecture on chapter 1.5 on voltage, current, and power. All right, so one of the biggest objectives with today's lecture is being able to apply the PSC, the passive sign convention. This understanding of this will make or break your time in this class. If you do not nail this down today or eventually, you're going to have a really tough time in this class. So I want to really make sure that you understand this well and practice it until you don't have to think about it. This is one of those baseline electrical engineering skills that's going to make your life so much easier once you take the time to understand it. The other thing that the second part of that is once you understand the PSC, how do you actually determine whether a component is consuming or providing power? All right, let's talk a little bit about current convention. Now, current convention is about the movement of electrons. The weird thing about electrons is that they are negatively charged. So, the traditional convention for a circuit like this with a battery is that the charge starts here at the positive lead and flows around to the negative lead. That is traditional convention. Now, here's the weird thing. What's moving? The electrons are moving. Electrons are negatively charged particles. They are attracted to the positive lead. That means they actually flow this way. And your physics instructors will fight tooth and claw. They're just going to fight tooth and claw, full on. That traditional convention is wrong, and flowing around this way is right. And that is a choice. However, current convention, really what it comes down to, it's arbitrary. You can decide which way is positive and negative, and you get all the arrows and decide how you want to do this. If you get a negative current, what does a negative current mean? It means it's opposite of the direction that you drew. It's arbitrary because, depending on how you look at it, it's half a dozen or 6. You get a negative convention, hey, I arbitrarily said it was flowing this way, it's flowing the other way, it's -3 amps. How fast is the current moving? Well, the cool thing about current is, the weird thing about current is that the actual drift speed of the electrons, that's how fast they move through the wires, is actually pretty slow, 1 millimeter per second, right? Now that's kind of fast, but why? Well, if it takes 1 millimeter per second, why when I hit the lights in my room, my incandescent bulbs come on right away? Well, the reality is the fact that the electric field that pushes those electrons along moves very quickly. Kind of like when you turn on the shower, right? You turn it on, water comes out of it immediately, right? Because of the pressure, right? Those electrons move very quickly, right? It's just like, hey, what's causing those electrons to move through your shower? It's a pump. Where's the pump? It is way, way, way downstream from where your house is, right? That's a better analogy. So the way that that electric field goes, that moves at approximately the speed of light. So it's really, really fast. For most circuits, we're going to assume that this basically starts flowing instantaneously. That's going to help us out a lot. If we were dealing with big circuits, this would be something we'd have to think about. But for our purposes, we're going to say, hey, you hit that light, that current starts flowing right away because that electric field is generated almost instantaneously. So these are the assumptions that we're going to make. Because we're traveling, these electric fields travel at the speed of light, we're saying the propagation for electric signals is instantaneous for the circuits that we're working on, right? The net charge stored in each circuit then has to be 0, right? What comes in, comes out. We're also going to assume that there's no EM coupling between components of a system. We're going to ignore induction. This is a pretty big assumption in some really sensitive circuits, but for the resistive circuits that we're looking at today and the stuff that we're going to be looking at over the next part of this quarter, it's a pretty standard assumption, and it's going to make things a lot easier. If we start looking at cases where coupling is really important, like radios and things like that. We're going to have to look more into it, but that's a lot more complicated topic. All right. So voltage is going to be one of the biggest terms that we're going to keep coming back to. We're solving circuits. We're often looking for this voltage, right? And this is the definition. It's energy absorbed or released per unit charge. Hey, basically we're talking about a potential difference here. That's the really big thing to remember when we talk about voltage. We're talking about potential difference. What is the difference between two parts of the circuit, right? What's the difference between this point and this point, right? The units for that come out to a joules per coulomb, or we're just going to call it volts, y'all. We're never going to use joules per coulomb. This might be something that we use to calculate things, but volts are what we're going to measure potential difference and always. Some things to remember about voltage, right? There's got to be a separation of charge here to have a voltage, right? Current, you do not have to have a current to have a voltage. That's not necessarily true, right? You can have a potential difference between two things that are not touching, right? Think of a capacitor, right? We've got two plates that are very close to each other. There's a voltage difference between the two plates. There is not a current flowing across that plate. That cannot happen, right? Well, it can if the capacitor fails, but a good capacitor, you should never see a current across the capacitor, right? That voltage is the pressure that pushes that charge through the circuit, right? So we have to have voltage to create current, but not current to create voltage, if that makes sense to you, right? All right, power, right? When we talk about power, we're going to be measuring this in watts, right? Power is a measure of energy that's absorbed in amount of time, right? Absorbed or supplied, right? So when we talk about electric motors, things that create or move energy, speaker systems, things like that, when we talk about that, we're going to be talking about watts, right? And using this chain rule, think about this. If we know that power is dW dt, and we know that our dq, that we're talking about wattage, which is dq dt, we can go ahead and use that chain rule here to figure out, okay, wait, breaking this up here, we've got dW dt, that's going to be voltage, and over here we've got our current, charge per time. This is going to look like voltage times current, right? You're probably used to using this formula. Power equals current times voltage, or voltage times current. And you'll notice that there is a plus or minus here, right? What does that plus or minus represent? Let's get into that. A plus or minus is going to be the basis of the rest of this lecture, right? Positive power for circuit elements is going to be absorption. Negative is supplying. I know, it's a little weird, right? You think it would be the other way around. I totally agree, but I didn't write these rules. Yeah, they wrote the rules for electrical engineering long before I was born, so I didn't get to make those rules. Absorbing power is positive, right? Because, I don't know, like to brag about your speaker system, you're never gonna say it's negative 600 watts. You wanna, using power is really cool, so it's a positive. Supplying power, it's a bit of a drag, right? It's going to be negative. All right, energy conservation. Now, the cool thing about energy conservation, because we assume that none of these things are storing charge, every watt that's absorbed somewhere in the circuit is being supplied, has got to be used by another element. We cannot create or destroy energy. We've got a closed system here. So net power supplied equals net power absorbed, or the sum of all those powers, positive and negative, is going to be 0 for the circuit. That's good. This is an equation that we can use to help us check our circuits. If this has always got to be true based on the assumptions that we've made about our circuits. So this is going to help us check our work. It's a really, really, really useful tool. All right, how do we find that energy consumption? Well, if we know power, well, we can integrate that dW dt to find out what energy W is, right? And that's going to look like, hey, what is our voltage times I And that's going to be at final time t, and also at time 0, right? We're assuming that this is not 0. Now, if this is a constant, right, we can take both v and t, v and I out of the circuit. This basically becomes a very simple equation. We can just say, okay, that's going to look like, okay, if we're saying, hey, if this is constant, assuming that this is going on, we can say, hey, our power just looks like v times I times t plus whatever our initial power is. We'll call it W naught, right? We know that this is 0. And sometimes we're going to make that assumption, hey, this initial power is 0. What is the power or the energy that's used in the circuit? We can say, hey, it just looks like power times time, if we're assuming that both our voltage and our current is constant. All right, let's stop there and we'll pick up this example in the next video.